Okay. Hi. So, ninth problem is a very difficult problem without knowing what dynamic programming is. So, let's go over what dynamic programming is to make sure we fully understand what is going on here. So, dynamic programming is a very fancy term of saying, hey, let's break the whole entire problem into smaller chunks or subproblems. So, basically, we just want to solve for each subproblem that we have. That's all the whole purpose of dynamic programming is. And this involves a lot of backtracking whenever you get stuck or if you reach something out of bounds and you just want to solve for every single instance of a certain quartile. So let's say, for example, we have a huge board, a huge matrices to say, and I just want to find a small chunk. So instead of solving for the whole entire board, let's take care of one subproblem, which is, let's say, the uppermost right corner here, which will focus on one problem that can be applied to every single other subproblem inside this matrix. That's the whole entire point of dynamic programming. We're going to do everything just once. And there are a few steps to follow. And so dynamic programming has a couple of steps. The first step is to define what are your subproblems. So first step is subproblems, basically breaking it down into one tiny chunk. And the next part is, hey, what is this recursive formulation? Or in other words, how am I going to solve this recursively? So we need to mark down recursive formulation. And then from here, we can skip time complexity for now because we don't know this is beyond the course material for data structures. But let's just focus on pseudocode. Pseudo, I misspelled this. Pseudocode. And that matters a lot. So let's take a gander at this small example, sweep robot. It's very common in algorithms and data structures. So let's cover this real quick since you might need this in the future. So a sweep robot is a robot that cleans a carbon model with an m by n matrix, and a carpet position at I and j will be 1 if that specific position is dirty. Else it'll be 0. It means it's clean. And the sweep robot will only start at cell 00, and we can only travel from round to right or down. And let's create a dynamic algorithm to maximize the number of dirty cells we visited by sweeping. So in other words, we have a little robot given this 2 by a m by n matrix. Oops. And we're going to start at the most left top corner. We're going to start here at 0, 0. And this little robot can only go two directions. It can only go down, it can only go right. And our objective, most of the time, is to clean up all the dirty cells inside this matrices. Or in other words, let's see how many times we can clean this up. So let's say we have a cell, let's say 1, 0, 1, 0, 1, 1, 1, 0, 0, 0, 0, 0, 1, 1, 1, 1, 1. This is going to be zeros. So let's draw this path real quick. So since we only go two positions, we can go right or down. Let's go here. Let's go to the right position, mark that as a 1, and let's go downwards since that's one of the valid positions. Let's go down again. Let's go to the right this time. Let's go back down, down, right, and then go back down one more time, and then go right, right. That's the whole entire point of this problem. This problem is just to clean up cells as we're traversing through this matrices. And this robot can go either right or down. So it can go either to 1 or 0. Doesn't matter at all. But since we want to get the most efficient number of clean cells, we're going to visualize that we're going to go to the right hand side first, then we're going to go down instead of going down right, since we want to clean up all the cells we can possible. And so that's a little taste of this problem. So to answer this problem, we need to denote a few key characteristics. First one being what is your subproblem? So your smallest subproblem ever will be given in a format like this. We can say that, let's say, max dirt, the maximum dirt, or let's say the maximum dirt cleaned, will at I and j basically denote the path that cleans the maximum number of dirty cells in n by n grid. So it denotes the path that cleans the maximum number of dirty cells. And then let's go over here, dirty cells. And we have to specify what's the size. And we can say in a m by n grid. Sweet. So our subproblem will be that an IOJ path, that IOJ will denote a path that cleans the maximum number of dirty cells in the m by n grid. Nothing else. Basically, we're going to define our function right here. Then from here, we need to call our recursive algorithm. We have to recursively call this again. So in other words, how are we going to call this function again to get the maximum number of dirty cells? That's easy. Let's create our function inside step 2. We can say max dirt for I and j, where I and j represent the indexes, just to be a little bit more clear. And since we want to find the maximum number of dirts, we can use a max function that will either go to the right hand side or it will go down. So we can just say max dirt. Let's go to the right hand side. We can say I minus 1 or I plus 1. It's completely up to you, as long as you make it clear which direction the robot's going. And we can say max dirt. If we want to go down, we can say I, comma, j minus 1. And from here, since we're going to try to get the maximum number of cells, we need to make sure we keep incrementing this based on your grid. So we can just say plus grid at I, j. And we can specify that the grid is a m by n matrix where grid I and j basically reuse some of the problem right here. And let's define what grid is real quick. So we can say grid is an array of m by n where grid I and j can be equal to 1 if can be as initialized to 1 if there is dirt. So basically if it's dirty. If there is dirt. Else it'll be 0. Basically saying it's clean. Nothing there at all. And so we kind of need to define some base cases since we're working with in a matrices. We need to make sure, are we going out of bounds or is this matrices just a one by one? If it's just 1 by 1, might as well just declare it as clean already because it's just 1 by 1. You're already standing inside that one cell. So let's define some base cases. For these base cases, we'll declare if we're going out of bounds. So let's say max dirt for I and j will be negative infinity because that will be a value that can never happen if we're ever out of bounds. So we can just say if the indexes are negative or j is less than 0. This is basically checking if it's out of bounds. out of bounds. Now let's check if we have, let's say, a 1x1 matrix. So basically like this, where the super robot, it's already inside this 1x1 matrix C. So since we cannot declare if it's clean or not, and the robot's already standing there, it's already done. Your job is basically done. Sweet. So we can say max dirt for 0, 0 is equal to grid of 0, 0. Because that's basically where you're standing at already. You're already starting there. And you're always going to start at the top right corner for this problem specifically. So if you're already there, declare it as 0, 0. And so now let's work on the pseudocode. Because for now that we have assigned every single variable inside this problem, and we have thought about every single possible case. So basically, just refresh. This will declare if we're going to the right hand side. And if that's not the biggest variable, we'll go to the bottom. So go down. And between these two variables, one of them has to be the greatest one because we want to maximize the number of clean cells we have. We'll take the maximum, and we're going to keep incrementing this value into our grid for this specific position. That's all we're doing here to maximize the number of clean cells we have in this n by n grid. So let's put this into pseudocode. First of all, since dynamic programming heavily involves in not repeating ourselves, we need to declare a cache variable, which will not be needed for this homework, but just a good practice to have. So we can just say, okay, we're going to have a cache where the cache will basically default all the values to 0, 0, or in other words, basically where I'm starting at, that would be 0, 0. So we can say 0, 0 when floor or grid is at 0, 0, because we're starting at that position itself, so it's already clean. There's no point in making it dirty at all because we're basically on top of that, and as a robot, we're cleaning it. We're cleaning a tile as we are on that tile, so there's no point in making it 1. So we're just making that grid 0, 0. So now from there, let's declare a function, and we call this max dirt. And this little function will have to take I and j. And the first base case is saying if we're out of bounds. And if we are, we're done. Return -1. It will never be counted as a variable we want to include. So it'll be I less than 0 or j less than 0. And for this case, since we want to find the maximum value, we'll return -infinity because that will never be max in any possible case. And since the programming involves not repeating ourselves, for this problem only, for the homework, we'll basically work around that. We can just say if I and j is not in cache, then we can basically just calculate this exact position and save it into cache itself, which will basically hold mostly every single position here for every single variable. So we can say cache at I and j. Yes, this is a valid pseudocode. It will just basically save that position at that specific cache, but completely up to you how you want to write this. And we can just call our recursive formulation here. We can say max. We will either go to the right hand side, so we can say max dirt. We can say let's go to the right hand side and see if that will give us the most clean spots ever, or let's go to the bottom. Let's go down. So we can say max dirt. And since we're going to go down, we need to de-increment j itself, j -1. And then from here, we need to make sure we keep saving this variable based on grid as well. So grid I, j. Sweet. And then from here, if we know this position is already in cache, let's just return this cache to say this is our maximum number of clean cells we have gotten. So we just say return cache at I, comma, j. So a few takeaways we should get here is that dynamic programming always calls itself, which is done here and here. This is done recursively. This will solve itself recursively. So your job and your only job for this problem is just to do one subproblem at a time and take care of all the base cases. So if we're out of bounds or if we are standing in that exact grid, there's no point. Save it 0, 0 or make it negative infinity. And then from here, this problem is done. We're basically all done here. This will solve itself recursively, and it will recursively find the maximum number of dirty cells we have cleaned as we return cache of I, comma, j. That's literally it. And I hope that will get you a little bit mentally prepared for how we're going to solve this dynamically wise. Since this problem, we're going to solve the Knight's Tour. The Knight's Tour is a very common problem that we need to use backtracking for. And since we're going to have to use backtracking, there's multiple ways to solve this. We can use queues, stacks to save the next move, making sure we don't go out of bounds, which is kind of something we took care of, except we're going to modify our return statement a little bit more. And since there's a case where we can do this dynamically wise, let's do it dynamically without a cache or stack that we have to code. We can just do it within a dynamic environment. So let's read it real quick. So your task for this homework is to create a C++ program that explore the Knight's Tour. And it's basically in a game of chess, the knight can do an L-shaped move as we're going to show below. And the whole entire point of this problem is basically to make a path for the n by n board where the knight will visit every single square exactly once, no repeats, and that's a definite thing we have to worry about. So let's make sure we save that here. And a tour is closed whenever the knight returns to its starting square formation and it continues loop through the board. So basically we have a loop path that the knight needs to take. Super important as well. So let's first break this into somewhat smaller subproblems. Let's worry about the loop we'll put that on hold for now, but let's take care of the L-shaped moves because that's our restriction. So an L-shaped move, of course, will have at least 8 possibilities and is denoted inside your homework as A, B, C, D, E, F, all the way until you reach H. So it's roughly about 8 possible moves you can do for that single square. So you can say 8 possible L-shaped moves, which is really important to declare this as 8 because you cannot do this 10 times. You're going to do this 4 times. It will always be exactly 8. And especially if we're starting, let's say, in this right-hand corner, we're going to have multiple moves that will be out of bounds, or it will just be within range, but still an invalid move. So since the L-shaped move takes at least going to a row by one and going down or up a column, or vice versa, it'll go twice towards a row, either left or right, and we'll either go up or down a column. So we can say, in simplicity form, we're going to have a row that will either go plus or minus 1 or plus, and then our column will be plus or minus 2. Basically, we can only go left or right 1. We can go up or down a column, up or down twice in a column. Or another way of saying this, we can simplify we can simplify the next instance where we can say we can go left or right twice in a row, or we can go up or down once in a column, like this. So basically, if we trace out, let's say A is going 1, 2 across a row, but it's going up a column. So it'll basically be this one right here. Or let's say if we do this one, let's do position B this time, we can say 1, 2 up a column and then 1 across a row. So basically do this one down here. So these will basically take care all of our possible routes inside this problem. Here we go. And move this arrows right here. So these are our possible L shapes, and these are always going to be our only possible moves, as we will only have a possible L-shaped moves every single time. So with that in mind, let's keep that to the side when we are going to determine whether a move is invalid or not. And if it goes beyond this range, it will never be valid at all. No exceptions. And so now let's worry about the loop now. So a valid Knight's Tour will either complete a complete circle when it goes back to the initial square, or it will be invalid. Nothing else. And since, let's say, for example, a knight gets stuck and it almost completes the loop, we need to backtrack to the previous step we were in and then figure out our next possible move. That's how we're going to implement backtracking here. So let's say, for example, let's take a small grid. Let's do it a 3x3. And let's say you're trying to move, you start at this top right corner. Remember, we have 8 possible moves. So let's draw out all these possibilities. So we can go here, we can go over here, we can go downwards over here, and then from there we can also do, using the graph below because I have horrible memory. Let's redo this real quick. Okay, let's say we can go twice up, one to the corner, stay right here, go twice up, go to the opposite direction, do something for the bottom. So we can go down twice, one to the left, down twice, one to the right, and let's take it for the other possibility if we go one across and then 2 up or down. Let's go 1 across. Actually, just go 2 across because we went up or down already, and 1 up. Let's do something here and go back down to 1. Let's go up here and let's go back up by 1. So let's go like this, and same thing with the bottom one, exactly like this. So there's multiple possible moves, except only 2 are valid, either here or here. So you have to keep track which move you want to do first. And both of these moves will be completely valid, no matter which path you decided to take, as long as this middle variable remains a whole. So let's say x declares as a whole. And so, and then anything outside of the range, so this is out of range, this is out of range, this is out of range, out of range, out of range, and out of range. We also need to take care of that as well. We can say an out of bounds condition, saying if it's within bounds, we're good to go. If it's out of bounds, do not proceed. So hopefully that makes a little bit of sense. But let's say, for example, this is a hole right here. Then we're gonna have to backtrack to the next possible one. So this will make this move completely invalid. So we have to go to this one instead, right here, the only other possible valid one. And that's how we're going to implement backtracking for this problem right here. So with that in mind, let's declare our few steps. What is the subproblems? What is the recursive allocation, recursive formulation, and then what is our pseudocode? So let's do step 1, our subproblems. So we can say that let dp, since it's dynamic programming, we can declare this as any variable you want. So let's say dp it will be the row and column, and we will have to pass in, since this is some 2D matrices or 2D board, let's pass in the number of moves we can do, since we only have 8 restricted moves, and if we ever go past 8, we know we have reached the maximum number of moves we can do. So we can pass in move numbers. And this will basically represent the Knight's Tour. Knight's Tour. Represent the Knight's Tour. Let's say we'll represent whether our Knight's Tour can be completed or not. Yeah, let's go for that one instead. So let's say represent whether. I think I definitely misspelled that. Yes, I did. Whether a Knight's Tour can be completed. Knight's Tour can be completed from row at this specific position given the remaining moves we have. So let's say given move number moves remaining. To make it a little bit more specific, what is move number? Sweet. And now, given this sub-problem, let's think about the recursive step we're going to have to do. And so, since dynamic programming, we're going to have to scrape most of the actual DP aspect of this problem. Since this course doesn't go too heavy into this topic in data structures. Let's move on to the recursive formulation now, except we're not going to make it into one letter. We'll just break it out some different if statements. But since we have to break this down to multiple if statements, let's take care of basics real quick, since base cases are not too bad in this problem. Base cases. So one of them we have seen, obviously, is out of bounds. So we can say if it's out of bounds, so if row column is out of bounds, or we have visited this already. So basically, we can say already visited. Then we can just say, hey, if this is out of bounds and I've already been here before, just return false. There's no point in doing this again. So return false. In code, you can do this a little bit differently. You can just say, if my rows and columns are still positive numbers and they were within range and I haven't had visits before, return true. Just to make sure, depending on how you want to implement this problem based on the pseudocode I'm about to give you. But in code, it could be however you want to code it, completely up to you. And the other one is going to be, hey, is my number of moves within the range of maximum moves? And if we've gone overboard, let's check if it's closed or not. And if it is closed, it'll be returned true. And if it's not closed, it'll always return false. So take care of that specific base case. So we can say if my remaining number of moves is greater than my maximum moves I can do. So we can say max moves, then return or check if the loop is already closed. So we can have a little function saying, hey, is this Tor closed? So is closed Tor. This will check whether or not the Tor is closed already. So, and this parameter will just check if it's closed or not. So basically, just make sure you have the current row and column position you want to go to. You're at right now. Check, and then bring in the board itself, including the number of rows and columns the board has as well. So this will check if it is closed or not. Or I can add a little comment saying here, check if Tor is closed. And if it is, just check it or not. And if it's already closed, return true. If it's not closed, return false. It means you basically could not complete that tour. And if it is true, you're basically done it. Congrats. So now let's break down our recursive formulation. So since we're restricted to only 8 possible moves, let's create a recursive call that is within a loop itself. So we can say, okay, for each a possible moves, we can check if this is valid or not. So basically, we can check for each 8 possible moves. We can do 4 things for this problem. We can say the first thing, mark this with move number. So basically say mark this position with let's say mark row column with move number. Basically saying this is my number of moves I'm currently at right now, and I want to make sure that I'm saving this index with this move number to see if it works or not. And then we're going to recursively call. So now we're going to do a recursive call to solve for the DP problem. We have this subproblem we created earlier. So DP row column, but this time I want to increment move numbers by 1 to signify that, hey, this was technically a pending rule, a pending position, a pending move, but let's check if it's valid or not. And if this is successful, we're going to return true. Basically, we have done it. We have completed our call. Basically, if successful, then we're going to return true. Else, it has not been successful, or else we're going to, if this was not successful, we're going to backtrack by unmarking the move, by unmarking the move. So in other words, we're basically going to initialize this row and column again back to 0. So we can say row column equal to 0. So instead of doing this with move numbers, we're sending it back to 0. And then sweet. And then since we're gonna to not recompute some of these states, we can just store the whole entire solution inside our DP subproblem itself. So let's see this in actual pseudocode. Since in code it'll be a little bit different itself, but same principles are going to apply here. So let's check real quick. So we can say, let's create a function itself. Step 3, create a function. And this one can be called either softtor or it could be anything else, but let's do softtor. So I have a function called softtor, which is going to be our main function. And this function in here has a lot of parameters. We have rows, column, we have the move number that we declared earlier. We also have to pass in the board itself, the number of rows of column we have for this board specifically, so number of row, num column, and then And then we also did pass in the maximum moves we can do for this specific instance, nothing else. So we're going to take our first base case. So our first base case is going to be the following. So we can say if move number is greater than maximum moves, then just return then call into a function called is closed toward as we declared earlier. So return is closed toward, which I will let you write the pseudocode for this problem right here. But this will just check if the tor is closed or not. And this function right here will include the row and column, the current row you're at right now, the current column you're at right now, the board, and since we're passing in the board as I stated earlier, let's write down the maximum rows and columns we have for this specific board. So num rows and then num columns. This will check if it's closed or not. And then from here, we're going to check the next, we're going to declare a few variables here. Since it's C++, you have to specifically say how many moves you have. And for our case, we want to check the next move inside this column. So let's write it down explicitly. So let's say we have column moves, which is an array. And we also have row columns, row moves, which is also another array. In this array, let's make sure we spell it all the way. This array will only have 8 possible moves entirely. And since these two arrays will coincide with each other, let's take care of the possibilities of the plus and minus variables. So let's do the first plus or minus. So let's say plus or minus 2, comma, plus or minus 1, and then plus or minus 1, comma, plus or minus 2. So let's fill in every single individual one. It should be roughly about 8 possibilities. So let's keep going. So let's do 2, -1. The next possible one is -1, -2. The next one is -2, 1. And then from there, we have 1, 2, which are positive ones. And we have 1, -2, basically going to be the opposite of these two variables right here. And then the opposite of the other ones are going to be 2, -1, -2, -1. And the opposite of the following ones is -1, 2, and then our 2, 1. Exactly like this. So this will take care of every single possible plus or minus of L-shaped moves. That's the whole entire part of these two. So let's just write a comment down right here. All possible L-shape moves, as we discussed earlier. Sweet. And then from here, we can check the for loop itself. And since we're going to loop at least 8 times, and we'll never go more than that, based on our recursive formulation, let's do that real quick. Basically have a for loop that will go from 0 to 8, because we need to do this 8 times. 0 all the way until reach 8. And since this will need to do a few things, we have to check the next move. So let's declare the next row and column variables, and we can just use what we have. We used above the next move, the number of actual we can use the all possible moves for L shape. We can use all possible L shape moves. My bad, got a little bit twisted in my mind. So we can say next row and next column will equal to my current position. So the current row I'm at right now, the current column I'm at right now, and we do plus our row move at that specific instance. So we can say row move of I, and then column move at that specific I as well. So we can keep track of all possible instances of rows and columns. Cool, cool. Now we're gonna check, is this valid or not? And if this move is valid, as we did earlier up here, if it is valid, let's keep going. And if it is out of bounds, like these variables over here, we cannot, we have to reassign this, or we can never do this at all. So let's see this real quick. So let's do if valid. Basically, we're going to pass in a few variables as well. So we can check next row, next column, and then pass in the board again, since we have to make sure we're using the exact same board every single time. And since we're going to pass in the board, we need to make sure we give them the number of maximum rows and maximum columns we have. So num row and number of columns. Sweet. And then making sure I did not pass the same variable type. I think I misspelled the S, but it's fine. It's pseudocode. Nothing to worry about here. And so if this thing is valid or not, and remember, if it's successful, we need to now check this recursive. We need to mark it now, call it recursive, and if it's successful, return true, else do reset, use backtracking again. So let's do this. So let's say, let's mark the board first. So let's say board at this position specifically. So next row and next column is going to be equal to my move number I have currently. So let's say I am at 2, so we mark this as the second move we have done in this board. And then from here, we need to recursively call our DP. But for this case, our new function recursive call will be solve tour. So let's just recall solve tour as our DP. So let's say if successful, so if solve tour, and remember, since we're going to do this recursive call for DP, our DP had the following. We had row, column, and then move numbers plus 1. Basically increment to the next move itself and see if that's a valid move. And so since solvetor has a couple more parameters than our DP initially had, let's make sure we do it correctly. So we do row, we do column, and move number plus 1, since we want to check the next possible move. And then from here, we have to pass in the board, the number of rows we have, number of columns we have. Yeah, it's pretty big, not gonna lie. And then our maximum move we have. So max move. And remember, if this if statement is successful, then return true. You're done. Basically, you have checked every single possible move. Nothing is wrong with this board at all, and you have created a closed loop. Return true. Else, return backtrack again. So remember, we took care of the first step, so we've taken care of marking it, calling this the recursive call, checking if it's successful, return true. Now let's do the backtracking. So we're gonna backtrack by marking a move row column back to 0, making it back to unvisited. So else board at next row and column, and then next column. Oops. Will be equal to 0. Basically, we are going to reassign this variable back to unvisited because it didn't work the first time. And since there's a case where we go over 9 or reach, the maximum number of L-shaped possible moves inside this loop. And if that's ever the case, just return false. That means it's not valid at all. The move is completely invalid and the tour is completely broken. So at the very end, return false, since we know this will never work at all. And that's basically it. You're done. This is our pseudocode for this main solve tour problem. And this will take care of the smallest sub problem itself. So let's do the first row, and let's draw it out manually. So let's copy and paste this real quick. Make sure we're using the right one, and let's use our algorithm we just solved right now. So let's duplicate this, and basically delete everything from this position, and let's start with the hole being at the middle again. But for this problem specifically, let's make sure we're following what we're given in our example in the homework PDF itself. So let me pull it up real quick. Okay, sweet. So our homework problems told us that this is not going to be position 2. So let's redeclare this as 1 over here as our starting position, and we took the bottom, we went down and we went across by 1. So this is now 2. And now 2 has a lot of possible places it can go to. So it can go down by 1, go across by 1, go down, go to the left hand side, and go up and go across by right, go up, go to the left, and it can also go across and go up, go across, go down, go across the other way, oops, and then go up or go across and go back down. But there's a problem here. And our algorithms are taking this already. So if it's out of bounds, this like these 6 points over here, what do? We basically just say it's not valid. So this will never be true. So we will never mark that as a possible move. However, we have 2 possible moves. We have 1 and we have this point over here. Remember, and this is valid function right here. We'll also check if we have visited that already. So let's 1 we have visited already, so that will never be marked as a possible spot. However, the lonely dot right here will be marked as a spot. It'll be marked as 3 as our next possible spot. So now let's duplicate this one more time, and we make sure we are going to check the next algorithm, the next position itself, which is going to be 3. So again, we have to do the exact same steps, but let's clean this up real quick. Sweet. Now let's do the exact same steps again. So let's go up, go to the left, up, go to the right, down, let's go to the left, down, let's go to the right, go across, go down, go across, go up, go across, go up, go across, go down. And again, there's only one possible move because all the other points are out of bounds, and we have visited 2 already, so this will be marked as 4. Now we do it again. One more time. Now let's start from 4 this time. So let me clean this up real quick. And one more time. Sweet. Now let's do 4. Now 4 has the exact same thing, 8 possible moves again. So let's do it one more time. Up, right, this time. Down, left, down, right, across, up, across, down. One more time. Across, up, and across, down. And so for this time, the exact same thing we get. Everything's out of bounds. We have visited that already, so we can mark the other one as 5. And almost done, I swear. It's a pretty long video from what I'm guessing. So let's clean this up one more time, making sure our whole entire algorithm works in case we need to backtrack. But for this problem, spoiler alert, we don't need to backtrack that much anymore. So one more time, let's do if we're out of bounds. So let's go up, go, oops, did not mean to do that. Go up, go to the right, go up, go to the right this time. Go down, go to the right, go down, go to the left, go across to up, across, down, across, up, across, down. And again, as our algorithm states, if it is out of bounds, it will not be true, which is done right here. This will check if it's out of bounds or we have that already. That's one support of that is valid function. So write a little comment down here saying out, not false, if out of bounds and or actually let's put and statement and visited already. So that's the whole entire point of that is valid function right there. It will check if it's false only if it is out of bounds or if it has been visited already. And our function right here will say, hey, everything's been visited except this lonely spot right here where 6 will now go to. We'll mark that spot as 6. And we call the function again, checking what's out of bounds, what's not out of bounds. So one more time. Getting tired saying all these out of bounds things. But we're almost done. So let's do 6. So we can go up, left, up, right, down, left, across, up, across, down, across, right, across, up and down. My bad. And again, all these are out of bounds except one variable, 7, right here. So recursively mark this as 7, and then recursively call this function one more time. Duplicate. And now we're going to call this function one more time. Let's do 7. So 7 has 8 possible moves again. So we could go across left, across right, down left, down right, across up, across down, across up, across down. And again, everything's out of bounds or everything has been visited already, like 6 in this case. So we can finally say 8 is our final variable that we have visited. But now we have to check, is this our last remaining variable? And when you do this recursively, it is. Because remember, you're doing this, you're going to check if the next column row is completed. So let's do check, because with algorithm states, we need to keep going. So let's say up across, up right, down left, down right, across, up, down, up, and then back down again. However, there are no possible moves we can do at all. All of it is invalid. So, if that's the case, we're going to do this check up here instead. We're going to say, hey, we have reached the number of moves we can do possible, and recursively, we're going to get to 9 with move numbers. And once we reach that final state, we're going to check if the tour is closed or not. And as we said earlier, this will check if it's closed or not. And let's check real quick. So we can go back to the starting position using the green as we do it right here. Let's actually erase one of the greens and just move it with purple. What purple will signify that yes, we can go back to the starting position. Thus, we completed a circle. This is a valid board. And so we can have a check saying, hey, if it's possible to go back to the starting position, we're done. And it is true. That is exactly correct. You can make it back to 1. And since we don't need to go back to 1, we can just state, hey, this board is our final answer. Duplicate this one more time. Delete all of this, including the extra curly brace, the extra lines. Perfect. This will be our final output. This is exactly what we're looking for. This whole entire thing is our output. Final answer. And that's it. You're done. You have completed the hardest part for Knight's Tour. You have given the dynamic pseudocode for this problem. But now for your homework, you need to do the remaining functions. Checking if it's valid or not. Checking if the tour is closed. Creating the main CPP function itself. And making sure you have the draw board from the last lecture. But hopefully that was useful for the beefy part of this problem. And yeah, if you have any questions, let me know. I'll probably be on Discord still. But hopefully you can see this and say, you understand this now. And I hope if you don't, just drop me a question. I'll be happy to answer it. But yeah, thank you for watching. Bye bye. Oops.